And welcome to Retro 48K. I'm back with another technically correct video, and this time it's Nintendo's entry into the 5th console generation. It's the N64. It feels only fitting to cover this one now, seeing as how a couple of weeks back it was the console's 25th anniversary. That's right, it was released way back in 1996, and it's a console that, at least for me, is largely famous for some amazing 3D worlds, but more so its fuzzy, or in some people's descriptions, fugly graphics. It famously started life as Project Reality way back in 1993, before them going on to be called the Nintendo Ultra 64, to finally just being called the Nintendo 64. And it's actually based on Silicon Graphics technology, with the founder of Silicon Graphics, Jim Clark. He actually offered it to Sega first before Nintendo, but Sega of Japan were unimpressed. Sega of America liked it, Sega of Japan were unimpressed, and due to issues to Sega wanting an exclusive license to the chips, meant that Nintendo actually won out, because they were quite happy just to license the technology. Now, I only mention this, I don't usually cover the sort of political side of things in these videos, but I think it's important in this one, and I'm not going to go into any more detail, as it's Sega of Japan versus Sega of America is an entire video on its own. But it's important, I think, for that Silicon Graphics connection here, because if you've watched my Dreamcast technology video, then you'll see some similar ideas here, and I'm assuming that Sega's interaction with Silicon Graphics at this time kind of informed the direction of the Dreamcast. It was probably much too late for the Saturn, especially with Sega of Japan's plans, but it probably did inform them a lot of what they did with the Dreamcast, and hopefully you'll spot some of the connections there. But anyway, that's enough about Sega. It's time to get on with what you're here for, and that's the technical breakdown of the N64 and how it actually worked. First up, for the architecture, I'm just going to do a brief overview, and then we'll get into each part in more detail. At the top, we've got the CPU, and now that was a 64-bit NEC R43000, which was a massive 93 megahertz. That is some serious horsepower this console had. It was capable of over 100 million instructions per second, with some sites actually quoting up to 125 million. Now, just to give you a bit of an idea for comparison, the two CPUs on the Saturn combined were only capable of 74 million instructions per second, and the PlayStation was only at 30 million instructions, so this was some serious horsepower it had. Connected to that was the real heart of the N64, the Reality coprocessor. This was to the N64 what Holly is to the Dreamcast. This is just the general heart that everything flows through this. This is the real beef of it, and it's probably what I'll cover in most detail. And then below that you had 4 megabytes of memory. Now, at first that might seem massive when you compare it to the Saturn PlayStations, but you've got to remember this was unified memory in the N64, so it didn't have VRAM or anything like that. It had the odd bit of cache here and there for texture memory and things, but in the whole, it just had 4 megabytes of memory. It was one big lump, and developers could do with it what they wanted. If you wanted a ton for the game but not much video memory, you could do that, or vice versa. It was entirely up to the developer, which gave them a lot of freedom, but also came with that cost. You had to balance that yourselves, and it was actually really forward thinking, because this is a model that the PlayStation 4 and Xbox One also followed suit with the unified memory. And then connected to the Reality coprocessor, you also had the game cartridge itself, the cartridge interface. Now, game cartridges could be anywhere up to 64 megabytes, which was about a tenth of a CD-ROM, and in fact most carts were between 16 and 32, so it was like a 20th of a CD-ROM, so not a huge space on the cart. And contrary to what a lot of people think, code wasn't executed on the cartridge. The cartridge basically, the information had to be read into memory and then dealt with there. The speed of cartridges came in that cartridge interface was much faster than reading off a CD-ROM. It wasn't the fact that it executes on the cart. And then finally, on the other side of it, you've got your video and audio DACs, the digital to analog converters. So these are basically what take the digital information and convert it to an analog signal to go up to your TV. And that's pretty much it. That's the overall high-level architecture of the N64. It looks relatively simple, but there's various buses and things connecting them. The real core and meat of the N64 is what's going on in that CPU and the Reality coprocessor. So first let's have a look at what that CPU is doing. So first up, let's talk about the CPU. This is what gave the N64 its name. It was 64-bit, and that meant you could do much more complicated and accurate, and that's the keyword, accurate calculations than 32-bit ones. It means that you can be much more precise. If you think about a CPU is basically doing maths all the time, those 64 bits mean you can have either bigger numbers or more precise numbers with more decimal points after them, etc, etc, etc. And if you're doing a lot of calculations in 3D, the more precise you can be, the more accurate you can be with knowing where things are. So it just gives you that extra added bonus. And just to give you an idea of how that works, in 3D worlds, the CPU is keeping track of everything. It needs to know where all the hitboxes are, where all the objects are, the interactions between those. Even if it's not on screen, the CPU needs to know about these things. Just because an enemy's on screen doesn't mean that its AI doesn't need to run, because it needs to bring the enemy on screen at the right time. That's really the difference between the CPU and the graphics card. The graphics card is just looking at what's in the camera. The CPU is not only running the world and the game logic, it still needs to know what's on camera and what is interacting with what as the player controls it. But the thing about the N64's CPU, which for me means that I don't class it as a true 64-bit CPU, because it didn't have it wasn't capable of addressing 64 bits of address space. It was only 32-bit. Now what that basically means is when you address memory or RAM is usually divided up into locations, and the way CPU will access it, it will ask for information at a particular location. So it'll say give me what's at location 325, and that will be read back into memory. With 32 bits you've only got so much address space, so therefore you've only got so much of a list of memory you can look at, which is 4 gig. So there was no need for Nintendo to go above 32 bits in address space. You weren't going to have 4 gig of memory in the N64. That would be like you could store its entire library multiple times over if you needed more than 4 gigs. So I can understand why they didn't do 32-bit addressing. It's just pointless. It was never going to work. And in fact, even the 64-bit calculations, most developers actually used the 32-bit operation on there because it was faster, and memory limitations of 4 meg meant you couldn't have a huge number of objects in the world, so addressing all that space wasn't needed, but also the precision wasn't needed because you didn't have a huge complicated geometry or anything to do with that. So largely the 32-bit operations were used. I mean, I'm not saying 64 wasn't used, obviously in some cases it will have been, but largely developers just stuck to the 32-bit operations to really get that horsepower. Connecting the CPU to the memory is the heart of the system, the Reality coprocessor. This was Silicon Graphics' baby, and it clocked in at 62 MHz, so it was no slouch itself, and it kind of, at least from a high level, fills a similar function to what the Holly unit did in the Dreamcast if you've watched that video. It was responsible for running microcode, which basically produced the audio and visuals that you see and hear on screen, and also for interfacing with the various memory units and peripherals and things like that. And it can be thought of as 3 parts really. There's the Reality signal processor, which executes audio and graphics tasks. The Reality display processor, which is the graphics pipeline to render out those visuals. And then finally the memory interfaces dealing with transferring data in and out of the CPU and RAM, etc. And all these 3 aspects could run, in theory at least, in parallel. So it was quite a powerful setup in the right developer's hands. But what does all that mean? Well, if we start with the Reality signal processor, the RSP consisted of a scalar unit, a vector unit, an instruction memory and data memory, and it would use these to execute a series of tasks from memory in order to build up a set of display instructions, again in memory, that could be read by the Reality display processor. So the RDP was made up of a texture unit with 4 kilobytes of texture memory, a rasterizer which would convert triangles and rectangles to pixels, a color combiner which would blend colors together for transparencies and things like that, and the blender which was used to give the N64 that unique anti-aliasing, that soft look that you're used to, and also Z-buffering, which is basically so the N64 knew the depth of objects in 3D space. And these 2 components would be used to build the image and audio information to send to the digital analog converters to be displayed on screen. So if you think about it this way, if you like a piece of build your own furniture from IKEA or something, the RSP would be responsible for building the set of instructions in that frame buffer, and the RDP is basically assembling that into visuals that you can see on screen. Now obviously there's a lot more depth here, such as 15 or 20 bit color depth on pixels, and the number of pixels that can be looked at per clock cycle and things like that, and the degree of that you can actually run some of this in parallel, because some of it just wasn't feasible to run in parallel due to latency limitations and things like that. But hopefully that gives you a decent understanding of the general graphics process. And I think one of the important things here is the Z buffer, because the N64 had a lot of nice features that meant it didn't waste resources thanks to that Z buffer. So for example, if you've got objects A and B on screen and A is part covering B, because of that Z buffer, it knew what the depth was. It would assign a depth to things in 3D space, and it would know per pixel what was behind the other one, so it didn't have to waste resources drawing things that you would never see. And it also had some other nice features to support this, things like clipping, which would cut the ends of polygons that are out of view, so again the N64 didn't waste resources drawing them. Culling, which is a similar feature, and it would allow the removal of the things like the backs of objects that you would not be seen, and it would do this through either backface culling or volume based culling. So basically if you didn't see it, it didn't want to waste resources drawing it, and it was quite some clever features on that one. One area I do want to cover in more detail, however, is textures on the N64, because I think they contribute massively to that N64 look on graphics. And one of the features that the N64 had was bilinear and trilinear texture filtering, which is basically a process of scaling some textures. If you think about a texture on, say, a signpost, or on the side of the ring, or on something like that, on a wrestling game or whatever, if the camera gets really close up to that texture, it needs to be able to scale it up bigger than what the texture is, and if the texture is off in the background, it needs to be able to scale it down. So when I say background as well, I don't mean far off distance, I just mean slightly further back than what the texture would be intended to be for the right size. When things are quite far away, like the example I've got on screen, what would normally happen is MIP maps would be loaded in, which are basically lower quality versions of the textures. And it's why on some game, for example the original Half-Life, you would see kind of a line just in front of you between the lower and high quality texture, where that MIP map was used and the high quality texture was used. So bilinear filtering was kind of for that mid-range, where you're resizing a texture in proportion to the camera, and it's maybe going from a texture that should be 16 by 16 and you need to display it in 20 by 20 or by 14 by 14. It's the mid-range distances rather than the quite far off. The images on screen at the minute are just as an example of texture scaling for you to get the idea of quite how tricky this is. Bilinear filtering does that. Now, modern graphics cards would do this in a way of using 4 sample points. It's a mathematical process basically. It takes the 4 nearest sample points and then makes an educated guess on what that pixel colour should be. But what the N64 did, because again this was mid-90s and early 3D technology, it used 3 sample points. It used the current, the upper left and bottom right, and this caused N64 textures to have an almost distinctive hexagonal shape to the patterns on them in some cases. It's why emulators have a hard time dealing with N64s, because they're trying to apply a 4-point process to that 3-point texture, and you therefore get like really jagged edges on things rather than the smooth. Even if you run it at a high resolution, you'll get that jaggedness. And it was actually the N64 at the time was the only console to support trilinear texture filtering, but generally this really wasn't used that much because it halved texture memory, so it wasn't widely used. But the other thing about textures as well is it used perspective correct texture mapping. Now that's an absolute mouthful to say, but what it basically meant was you could have large 3D environments like Mario 64 and not use a huge amount of polygons, because you could stretch a texture across a large area and it would correct it based on the perspective. If you did this on the PlayStation, for example, you would have to have smaller textures and more of them and more polygons with those textures over them in order to do the same space. So if you've got a big floor, for example, The N64, you could have just one big texture across it. The PlayStation, you would get a lot of warping after a certain distance, so you'd have to carve that up with smaller textures. And it was quite a nifty feature that allowed big 3D worlds, and it's funny to think of a feature for textures that allowed bigger 3D environments. And it's one of the key things to understand about the N64. It was designed and built pretty much to play Mario 64. Everything else was kind of an afterthought, and that's kind of Nintendo's approach to a lot of hardware. They have a game in mind and they build a hardware to play that game and then see what they can do with it for other games. So in general, the N64 is an interesting beast. It was an absolute powerhouse, way above its time in sort of CPU power, and that unified memory was something we would come back to 20 years later, so it was really forward thinking in that respect. But it was held back with some other bizarre decisions, things like the cartridge size. While it didn't really affect graphics, it did affect audio in terms of the N64. You used the CPU or the reality coprocessor to generate audio, and it was capable of sample rates equal to that of the PlayStation. However, if you did that, you would probably fill up the cartridge space in no time at all, because you only had a 20th or a 10th or of the space. It was just really limiting. So on the audio side, it really did hurt it. And a lot of people think it hurt the graphics too, and they think that's the reason for the lower quality textures on the N64, but that was actually more to do with developer tools from the various homebrew sites and forums that I've read. It seems to be basically that developers like Rare and Nintendo and Factor 5 got access to the low level hardware, so they could use that 4 kilobytes of text to cache as they wanted, whereas other developers just got the standard developer tools, and they were forced to do things like you had to fit textures to the exact size of that cache, which the PlayStation wasn't limited to, so they would have to cut corners to get it on there. So that was more a tool set thing, and again it shows that the PlayStation's real advantage on this generation was having the right tools for developers to get the full power and potential of that unit. Nintendo weren't far behind them, but it really was that made the PlayStation different, that and the CD technology. But that kind of brings me to the end. I hope you've enjoyed this video. Have I got anything wrong? As always, if you think I've got anything wrong, please put it in the comments. I do like to hear back from you, and I will issue corrections on there. But what do you think of the N64? Do you think it's fugly? Is it one of your favourite consoles? It has some of the best games of all time, so I would imagine there's a few big fans out there. But as always, thanks for watching. I'm Retro48K, and I'll see you in my next video.